Hey, welcome back. So by the time that you're watching this video, it'll be Friday, which means that we've completed an entire week of e-learning. So congratulations to all of us on that. I did want to give you a small update on the spread of that coronavirus. Unfortunately, we have had our second death in the state of Indiana. It was another person that was over the age of 60 with pre-existing conditions. But it does kind of emphasize that we need to be taking this seriously, and we all need to be doing our part to prevent that spread. I also wanted to check in with you a little bit about our participation with the e-learning and how we've been doing. We had that first assignment, the ionic compounds set. It was due on Wednesday at midnight. I'm making this video on Thursday, so I just saw how many people turned that in. Most of you did turn it in on time, and I'm very happy about that. But I have 25 people in the ballpark that have not turned in that assignment at all. So it's really important that we are checking Google Classroom every day, that we're watching the video lectures, and that we're turning in our assignments. My first step is going to be to put it in as a 0 and send you an email to let you know that you're falling behind. And then my next step, if I need to, is going to be to make phone calls and reach out to your parents or guardians and ask them what's going on and why has your student not been completing the assignments. We are still in school, guys. This does still count as our education, and we need to be taking that seriously and not ending up with zeros in the grade book. We don't want that. All right, so what are we going to do for this last video lecture of the week? We need to finish out that covalent compound set, and I'm going to spend today talking again about oxidation states. It's going to be similar to the video that I made on Wednesday, but I've got a few new things to throw in there, and then at the end I'm going to talk a little bit about spring break and what it'll look like after spring break if we're still on this distance learning, this e-learning. All right, one more day for this first week. Let's get it going. Oxidation states. All right, so let's think about how to solve these oxidation states for covalent compounds. We're still going to use the railroad method that we used earlier. The difference this time is that we're not going to end up with those ionic charges that sometimes make the ionic compounds easier to do because the oxidation state will match the ionic charge. But in covalent compounds, we don't have those full charges, so it makes it maybe slightly harder to find the oxidation states. Let's do these 3 easier type examples first. So the first one that we're looking at here, CO2. We know that naming this, we're going to call it carbon dioxide. Setting up my railroad method, I will make my parallel lines, parallel-ish, that's fine. Make my little railroad track here. This is a neutral compound. None of the compounds that I picked have charges, they're all neutral. So I'm going to set it equal to 0. And then I'm going to start using my oxidation state rules. I have a rule about oxygen. Oxygen will always be -2. If oxygen gets those 2 electrons, it'll fill its octet, it'll be very stable. Oxygen is electronegative enough to do this in almost all cases. Carbon is my variable this time. I don't know what the oxidation state of this carbon is going to end up being. I'll multiply by my subscripts. So x minus 4, 2 times -2, -4, equals 0. So if x minus 4 is 0, I can say that x is going to be positive 4. That means that this carbon has given away 4 electrons, 2 to one oxygen and 2 to the other oxygen. That gives the oxygens octets, which makes them stable. The carbon actually has a duet here, which is also stable. That's going to be a good configuration for the carbon. Moving on to another example here. This one looks really similar to carbon dioxide. This is sulfur dioxide. So let's see if we can't solve for sulfur dioxide. It's going to be pretty much an identical problem. I ended up at the same oxidation state. The oxygen is still going to take 2 electrons to fill its octet. Sulfur is my variable this time. When I do a little bit of algebra, I'm going to find that the oxidation state of the sulfur is +4. Just like I had up here, +4 for the carbon. The difference between these two chemicals, carbon dioxide and sulfur dioxide. In carbon dioxide, the carbon does end up at a stable electron configuration. If I take away 4 electrons, carbon has 4 valence electrons, it gives it a duet that's stable. Sulfur dioxide, though, is not going to be quite the same electronically. When sulfur gives up 4 electrons, sulfur has 6 valence electrons, so it still has some valence electrons after taking away 4. 6 valence electrons, I take away 4. This sulfur still has 2 valence electrons. Call it a lone pair. We talked about that a little bit the other day. So this sulfur is not completely stable. It has 2 electrons in its s orbital. And that leads it to be just a little bit more unstable than this carbon is. That means that carbon dioxide is a fairly stable molecule. We breathe in carbon dioxide all the time, and it doesn't negatively affect our health. But sulfur dioxide is less stable. If it's less stable, it's more reactive. If we were breathing in sulfur dioxide all the time, eventually that would become too toxic for us, and it would lead to negative health impacts. This sulfur dioxide, I'm sure that you've smelt it before. Anytime that you strike a match, you make a little bit of sulfur dioxide. And it's less stable because the electron configuration of that sulfur is not at an octet. Let's try this last one here. SF6, sulfur hexafluoride. I'll set up my railroads. This is a neutral compound, so I'm going to set it equal to 0. I do have a rule about fluorine. Fluorine is the most electronegative element. Fluorine is king, or queen if you prefer. So fluorine is always going to have an oxidation state of -1. It wants to get 1 electron to fill its octet. It's the strongest element, the most electronegative element. So it will be able to get that electron every time. Sulfur is my variable. If I multiply by the subscripts, x minus 6 equals 0, x is +6. So this time, we've got a difference here between our sulfurs. This sulfur is at an oxidation state of +4, making it a little bit unstable. This sulfur is at an oxidation state of +6, giving it an octet, and that does make it pretty stable. Sulfur hexafluoride is also a gas, but this is a pretty stable gas. All of these elements have completed their octets, making it pretty unreactive. You can breathe in sulfur hexafluoride in safe amounts. This is the one that makes your voice really, really deep. If you haven't seen it, I recommend looking up YouTube videos of people inhaling sulfur hexafluoride. There's some good ones where they do drive-through pranks. There's a guy that beatboxes with sulfur hexafluoride in his lungs. It's a really cool sound effect. I would definitely check it out if you haven't ever seen it before. So these were my 3 easier type examples of solving oxidation states for covalent compounds. I want to look at a few examples that might be a little bit harder. I'm even going to give you one of the answers to your homework set. So let's get some new examples up on the board here, and we'll do probably 3 more. Alright, so I want to do 3 more examples of oxidation states with covalent compounds. So this first one that I picked here, this is iodine monobromide. Iodine monobromide. I'm going to set it up the same way. Make my railroads. This is a neutral compound, so I'll set it equal to 0. But now, I've got no rules to guide me. Iodine and bromine, these are elements that don't actually have the rules that go along with the oxidation state. So how am I going to solve this problem? I need to think about which element is more electronegative. The element that's more electronegative is going to be the one to take the electrons, or the one to get a negative oxidation state, I could say. So between iodine and bromine, bromine is further up on the periodic table. That means that it has fewer electrons shielding the nucleus. That's going to make it more electronegative. So bromine is stronger. Bromine is more electronegative. Because it's more electronegative, I'm going to let it complete its octet. I'm going to give it its common oxidation state of -1. Iodine's the one that I don't know here, but this algebra is going to be really easy. X minus 1 is 0, so X is going to be a +1. Normally iodine would like to gain an electron to complete its octet, but this time it's going to give up an electron to satisfy bromine's octet. That means that iodine monobromide, it's not a very stable compound. This iodine atom specifically is going to have a really unstable electron configuration, which is going to lead to this being a pretty reactive chemical. Let's try another one. Ni3, nitrogen triiodide. I'll set it up the same way. Railroads, I'm trying to get to 0 because this is a neutral compound. I need to ask myself, which of these elements is more electronegative? Nitrogen is going to be the more electronegative element this time. So I'm going to complete nitrogen's octet. I'm going to give it a -3. This is the common oxidation state for nitrogen. It's not one of our rules, but nitrogen is more electronegative. It's stronger. So I know that it will be the one with the negative oxidation state. Iodine's my variable this time. I've got 3 iodines, so I make it 3x. Doing my algebra here, I'm going to get that same oxidation state for the iodine. Up here it was at +1, down here it's at +1 as well. Having 3 iodines in this compound that are all unstable, this is an incredibly unstable chemical right here. This is actually an explosive, nitrogen triiodide. It's so unstable, so reactive, that you could touch it with a feather, and that's enough to make it explode into this big purple ball of cloud of smoke. Again, you should look up YouTube videos of nitrogen triiodide explosions if you're feeling bored today. It's pretty cool how they do it. It's just so sensitive. Just a little shock would be enough to set it off. Let's try this last one. I got P2S5, and we know from our nomenclature that this is diphosphorus pentasulfide. Diphosphorus pentasulfide. Let's solve. Trying to get to 0. I've got to know which one is more electronegative. They're awfully close, but the sulfur is more electronegative. I could look that up on a chart, It's also the one that's furthest to the right, which means it has more protons in its nucleus, which means it can attract electrons more strongly. So sulfur is more electronegative. I'm going to fill sulfur's octet, -2. Phosphorus is my variable. I'll multiply by the subscripts. 2x minus 10 equals 0. I'm going to get that x is equal to positive 5. So this time, the phosphorus is going to give up 5 electrons. Each phosphorus atom is going to give up 5 electrons, 10 total. The sulfur is going to gain those electrons. Each sulfur is going to gain 2 electrons for 10 total that sulfur has gained. So actually this time, the phosphorus has a complete octet and the sulfur has a complete octet. Diphosphorus pentasulfide would actually be decently stable, at least compared to these other compounds that we looked at today. So I know for sure that this one is one of the ones that I put onto the covalent compound set. And I just gave you the answer here for nitrogen and for the iodine. So if you're watching the video, you got a leg up. I just gave you one of those answers. Alright, so that's good for our lecture today. At this point, you should be able to solve all of the problems in that covalent compound set. And that'll be due at midnight tonight. Now, actually, while I was shooting this video, I just got news that our governor has closed down Indiana public schools until May 1st. May 1st. That's quite a ways away from now. That means that we're going to be on this e-learning, this distance learning, for a while, for over a month. I'm going to need to see some changes from you guys, and I myself am going to be implementing some changes too. What I'd like to see from you is more participation. Not enough people are watching my videos, not enough people are turning in those assignments that I'm posting. And then on my end, I'm going to work to make my lessons a little bit more interactive to give you a chance to participate more. I'm going to change the way that I do my lectures since we're going to move away from review and move into some new material. And there will probably be more assignments and more varied assignments. So be watching out for that. Check Google Classroom every day. Now, all that said, we are on spring break next week. So after you turn in that covalent compound set, you do get a nice week off. No lectures, no assignments. Just truly take this as a break. Do what you can to have a good time under these conditions. When we come back on the, I believe it's the 30th, yeah, on the 30th, we're going to start doing some new material. I'm going to need to test you on that week of the 30th, so we'll do an all online assessment and test. And then like I said, we're going to start learning new material through these video lectures. So it's going to be really important that you're watching the videos every day and that you're participating with your classmates and communicating in that way. We did these team building things at the beginning of the year. All of that is still true. So we've got to support each other. We've got to help our friends that might have those blindfolds on in their lives, and make sure that everybody is going to pass the class, even under these conditions. All right. I hope that you are not stressing too much. I hope that you're having a good time managing to find some fun in all this. And I hope that you are getting all your assignments done too. Enjoy spring break. Stay healthy. Stay safe. I will log back in after break, and we'll have some new material to go over. Stay classy, Artesians.